Hi everyone and welcome to a new video about controller design, and we continue with the subject of root locus method, and this is our example number 3. In this example we will look at the design of a PI controller, and we will look at simulations and calculations to verify our calculations in MATLAB. So let's look at our example. Now we have the following situation. We have a second order system which must be designed controlled using a PI controller, and this is a diagram we have. So we have the controller encapsulated with the plant and the transfer function of the plant, and the controller are given here. So the plant is a second order system, is already stable, so we have a -3 and -8 as stable poles, and the controller is given by this expression, which has a proportional part K1, which is just a gain, plus the K2 over S, which is done the pure integral part. So K1 plus K2 over S is the complete PI controller expression. So we will need to determine the K1 and K2. So design equations are given as follows. The steady state error must be 0 for step input. That means the following: the output Y must track the input R. So if I apply a signal here, must be, can be 5 volts. I need to have also 5 volts at the output. That means actually that there 0 steady state error for step input specifically. Now the overshoot must be less than 5.7%, and we need to have a settling time with a 2% criterion of less than 0.8 seconds. Now let's look at the solutions. How do we start? We need, of course, to work toward these two parameters K1 and K2 as our final goal. But before we can do that, we need to determine the design point, which is what we also did in the previous examples. Now for that I need the damping ratio, the absolute damping, etc. So I will start with the overshoot MP. Of course, take it as scale, not as a percentage, and then use the formula for the damping ratio, and then substitute in that the given value of MP. So the MP substituted in this, I will have then the zeta, which is damping ratio of 0.674. Now from the settling time of 0.8, I can determine the absolute damping, which is sigma of D, by calculating out 4 divided by the settling time. 4 over 0.8 will be exactly 5. So 5 radians per second is our sigma of D, which is also the real part of our design point. It will be developed shortly. The omega D is the imaginary part, and that is then given by this expression using geometry. Will be sigma D times the tangent of our cosine of this zeta, which is the damping ratio already calculated. So if I just substitute the values, I will get for the omega D, which is also the imaginary part, 5.55. Now from these values I can determine the closed loop poles, which are dominant, assumed to be dominant, and these are the following: S1, 2 will be then the minus sigma of D plus or minus J sigma D. So omega D, I mean. So we have then the S1, 2 is then equal to -5 for the real part, and a plus or minus J 5.55. Now for the design point, I will just take one of these dominant closed loop poles. I will take the one with the positive imaginary part. So that will be P1, that is just my name for the design point, is -5 plus J 5.55. Now let's look at it in a diagram. It will be a bit helpful. The P1 is located here, which has a real part of -5, shown here, and we has also an imaginary part of 5.55. So there is a design point here. There are also two poles from the open loop system plant, which are at -3 and -8, given by this two crosses. A cross is actually a location of the pole, and then the circle is just a location of the zero. It will be also discussed in the next steps. We need to design the K1 and K2, dus the PI controller, such that our root locus plot will cross this or comes nearby this point, so that we have the required specifications. That's actually our goal. So let's look at the next steps. We start with the root locus equation. So the root locus equation will be then used to calculate the required value for the K1 and K2. So let's look at it. So the root locus equation is given by this expression: 1 plus the loop transfer function is equal to 0. That is actually the root locus equation, where the L S is the loop gain. And this is given in our case the controller times the plant, and the controller is given by this expression times plant. So I've specifically made the controller red and also the plant blue. You can then distinguish more easily what is the actual system. So you have now the controller that can be also written in different forms. So the controller is given here as two separate parts added together. You can place it in just one fraction. You can also write it in a different form. It will be very helpful. You can then recognize that there is a 0 here, which is given by the k2 over k1, which is just a nice expression that you say, okay, there is a 0 and there is a pole at the origin. But in this form, I don't see that directly. So there is, of course, something here at the origin maybe, but I don't know if there is a 0 of a pole here in addition. So this is the best way to express your controller. Then we can say k1 is just a PI controller gain and k2 over k1 is the PI controller 0. So I will use that later on. So the expression for the loop transfer function will be then as shown here, and if I just simplify this, I just added this part in here, and I will simplify this by taking the 5 in the numerator and also the s in the denominator, and I will have this expression. So this expression is much more easily to use than this expression here on the top. Okay, then we have the following situation. If I now substitute this in here in the root locus equation, I will have this expression. I need to determine the k1 and k2. That will be done shortly using different criterion. So if I take the 1 here to the right side, I will get a -1 here. Now, since this is a complex expression, and that must be equal to -1, then we have the following. This is the loop transfer function, which is given in the S domain. I will have two conditions. One is the angle criterion. That means actually the following. This loop transfer function has an angle of 180 degrees or a -180 degrees. Must have this criterion because it says it is -1. That means the real value, the real part, just the real part is pointing in the negative x direction. The other criterion is the magnitude criterion. That means this has a magnitude or a length of just 1. This is the length of 1. So we have two conditions we need to match. So two criterion we can use to determine the k1 and k2 that makes actually these two criterion valid. So we will now proceed using these two criterion. So let's start with the angle criterion. Okay, before we start with the angle criterion, I will use this plot, which is now an extended version of the former plot I have shown in the previous slide. What you see is again the P1, which is our design point. We have the -3 and the -8, which are the open loop system poles. And we have the -5 and the J5.55 for our location of the design point. You can see there is a phase associated with this plant, the pole of -3. This is the phi1, and a phi2 is the pole associated with the pole at -8. Now there will be a 0, which is the, if I look at the controller, at k2 over k1, which is this, and this value will be calculated shortly. So this 0 is the -0 of the PI controller. There is also a pole, of course. This is the pole, but this is just at the origin, so we can see that this is at the origin, and it is the pole of the PI controller. And those have also associated phases, so we will use that later on. So the angle criterion says the following. If I need that the argument of this loop transfer function is equal to -180 degrees, I must say that all the phases together, summed together, must be also -180 degrees. So if I have the phi1 and a phi2 and a phi pi and a phi zpi, I will then equate that to -180 degrees. So I have just written down here the phi of pi, but if I work it out, I have then this. Now there is a one note here that's important. The phases of the poles are negative, taken negative, because the poles are always in the denominator, and the phase contribution of the 0 is always positive. That is actually why we have a minus sign here before actually the phi1, phi2, and also the phi p of pi. The only plus is actually at this 0, so you can see that here. So if you have this, then you have actually the correct statement. Now the phi1 is the phase contribution of the plant at s is equal to -3. Again, the phi 2 is the phase contribution of the plant at S is equal to -8. And the phi of pi is the phase contribution of the pi 0 minus the phase contribution of the pi pole. And which is the required phase contribution for our design that must be provided by the pi controller. With, again, this is the phase contribution of the pi 0 and this is the phase contribution of the pi controller pole. So how do we calculate phi of phi 1? So this one. Now you can do that more easily by calculating first this part, so actually this smaller part, and then use 180 degrees minus this angle. That's actually what's shown here. So it is 180 degrees minus arctangent of this height divided by this length. So it is 5 minus 3 just in the absolute sense, and you will have this expression that will be approximately 110 degrees for phi 1. And a similar form for phi 2, but this is of course a smaller angle than 90 degrees, so I don't need that 180 degrees action here. So that is just 5.55 here, just the height divided by this length here. In this case it is 8 minus 5, just the absolute value of this distance. So we will have then 62 degrees if you do the math here. Now the pole of the pi controller is also located at the origin, so I can also calculate that. That also requires 180 degrees minus this part, which is done here. It is again the height divided by the length, which is in this case just 5. So 5.55 divided by 5 of arctangent, and then do 180 degrees minus that part will be 132 degrees. So I can now collect the phi 1, phi 2, and also the phi of pi, phi of the pole of the pi in here, and then I have the following. And I can then calculate the phase contribution of the 0 of the pi controller. So I will just substitute the values. I have then the following. So the 0 of the pi must contribute a phase of 123 degrees. So what we have is in the following. I look at the location of the 0, which is here, and then I can say it is also a phase contribution. It's also a calculation using 180 degrees minus this part. So it is the half circle minus this part of the angle. So it is 180 degrees minus arctangent, the height divided by the 5 minus that location. We don't know yet. It is given already here the answer, but this is the calculation you really need to do. So what you then get is the following. So it is just substitute the values, and you will have then the 0 of the pi, which is then given as 1.34. The 0 of the pi is 1.34, but of course, if you look at the left-hand plane, you of course always take the negative side of that one. So this is our 0. So this 0 is already set is this expression k2 over k1. So that means actually these are equal to each other. So that means, so the k2 over k1 is the 0 of the pi controller. That means k2 over k1 is equal to 1.34. So the controller in this case is then given by this expression k1 times s plus 1.34 for the 0 divided by the s. That is actually the controller expression we have at the moment. So we still need to calculate k1. So let's look at what we need to do in the next steps. So we will use also the magnitude criterion to calculate the k1. So the magnitude criterion is results from this, so that we have a loop transfer function must be equal to -1. That will of course result in the magnitude, which is just equal to 1. Now if I again use the expression for the loop transfer function with the 0 I have just determined, I have this expression. So I have then the following situation. The k1 is equal to this, so you just do the math here for yourself. And if I now evaluate the k1 at the design point we have determined already, then I have the following. So I just substitute for s1, s I mean p1. Just everywhere where you see an s, I just substitute P1, 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 so 4 times P1, and then just substitute the value, actual value in here, and then take the absolute value of that one. That will result in the following expression. So we have then the square root of this part with the squares of the real and imaginary part, etc. for the other two parts, and also for this. You will have then, if you do the math here correctly, 8.36 for the K1. So we have already the value of K1. So that is one of the unknowns for our controller. So what we have then, having calculated K1, I can now calculate K2. Why? Because I know that K2 over K1 is 1.34. Thus we get the following. K2 is then equal to 1.34 times K1, which is 1.34 times 8.36 equal to 11.21. So the PI controller in this case is then given by this expression, which is then given by this expression in the original form. If I, of course, want to rewrite this, I can write it in this form. But if I wanted to write it in a much better way, with the zero and the pole directly recognizable, I have then this expression, which you can see the PI controller gain is 8.36 and the PI control 0 is 1.34. So this actually will be used as our controller for our PI controller. So this is actually, the conclusion is, this is the controller for this assignment. Of course, we need to verify this because this is what we have done, and the root locus method assumes that our dominant closed loop poles are dominant and they will define or determine all the dynamics in the system, and that might be not true. So we need to verify this using the simulations. So let's look at it also in the simulations part. So the simulations, I have the root locus plot of the closed loop system with the PI control we have just determined. This is the closed loop, this is the root locus plot. What we have is the poles actually of our system, what we have designed for. So actually these are the two dominant poles. I can see that there's a one pole here, so it might be the case that we have not the exact performance as we expected. But if I look at these two poles, dominant poles, I see that the location here, which is given here, is -5 plus 55.55 I, which is actually the J what we use in our calculations, which is exactly what we had. And the damping ratio is 0.669, which is very close to 0.674 what we had. So it is very close to what we have calculated for our design point and also for the damping ratio. So let's then, this is the summary, let's then look at our unit step response, because that really determines how the performance is. This is unit step response. Okay, what we see is, I see a step response with a settling time of almost 2.7 seconds, which is way larger than the 0.8 seconds, so that's definitely not the best starting point. So this is not good. And I also don't see an overshoot, so I had some headroom for my overshoot, which was 5.7%. This is 0, so that is actually too good. But I have a settling time which is 2.7 seconds, which is too large. So we try to optimize this. So this is in the first round not what we want. So overshoot is 0%, but the settling time is much larger than 0.8 seconds. So we need to redesign this. So what we can do is, for example, we can adjust the gain here of the PI control. So I made that from 8.36 to 14.03 by just tuning in the MATLAB. So I have then the following root locus plot with the location of the poles, dominant poles here, and I have then this current location of our dominant poles, and this is damping ratio. You might say, is this better than the first original controller? I think so. Why? Because this pole, which is the third pole, is now close to those 0 of the PI controller. So if the 0 and the pole, of course, come close to each other, you will have the effect of the pole not as strong as before. So the effect of this pole will be eliminated, or in some sense partially eliminated by this 0. So if this is approximately at here, then it will have less effect. So I think this has a better performance. So let's look at what we have here. So this is a summary of this So unit step response of the closed-loop system with the tuned PI controller, and again only the PI controller gain is adjusted here. This is what we have. What we see is the overshoot is almost 0%, so I assume that it's just 0. There is settling time, it's smaller, it's 1.92, but still too much. Okay, I gained something, so settling time is a little bit smaller, and overshoot is still 0%, so I have still some headroom here, but still is not what I wanted. So this is the PI controller. Okay, you can maybe do the job, but it is not what I wanted. I have also done this using increasing this gain, but also that didn't work out. So this is actually what we can do at best, just tuning the PI controller gain. So this is okay, that's fine, but the settling time is definitely not fine. So, and it's the result what we have here. So we need to redesign this. So let's look at it in more detail. Now I will now set the root locus plot in the unit step response of the closed-loop system with a tuned PI controller now next to each other, and this time I just keep the PI controller gain as the original case, which we have designed in our calculations, but I've now shifted the 0 from 1.34, that's actually what it is, so from 1.34 to 2.52. So I made the shift to the left side. So it's approximately 2 times larger. So what we have then the following plot. So we have the root locus plot with the poles given here, and this is actually the region, the yellow region actually where you don't, where it is not allowed to be in the ideal case where you have just only 2 poles and no zeros at all in your system. If I look at the performance, look at the performance on the right side, just unit step response, I can see that the overshoot is 3.21%, which is less than 5.7%, which is okay. And I see that the settling time is 0.765, and that is also less than 0.8 seconds. It's all at the edge, but it is less than what is maximum allowed. And I also see that the final value is 1. That means actually, since this is a unit step, so I apply a unit input, I get a unit out. That means there is also 0 steady state error in it. So in total, that's also fine. In total, I have an overshoot which is less than 5.7%. I have a settling time which is less than 0.8 seconds, and I have a final value of 1. That means the 0 steady state. That means a 0 steady state error for unit step input. So that means the design is in this form completed actually using this controller. So I have only made the change in the 0, and that have resulted in this expression. You can of course go on with maybe also the gain and improve that even more, but that is actually what I have at the moment. What you see in the root locus plot is that the poles, the closed-loop poles, which are given here as pink dots, are not actually in this white region. And that's not always the case if you just assume that the 2 poles will determine your dynamics of your system. So this pole will definitely, and also this 0 will definitely determine your dynamics. So this is a first step in your analysis, but the actual verification is of course done with a simulation in MATLAB, and that's actually what you need to do in your design cycle. So let's also look at the summary. So what we have done in total, we have designed 3 controllers, and I have now plotted here the T1, T2 and T3, which are the closed loop systems with the associated PI controller. So T1 is the PI controller. T1 is, I mean, the closed loop system with the PI controller in the original design, and T2 is the one with the adjusted PI controller gain, and T3 is the one with the adjusted PI controller 0. So we have now all of them together. And this is a table where we can set up. So this is the first controller, second controller, and the third controller. What we have here, that must be of course GC of 3. So we have then this one. We see that there is a settling time which is much larger, and also settling time is much larger. But this is of course according to the specification. So we will use this, and that means the design is completed for this exercise. So the exercise is now completed. Again, as I said before, we have designed the PI controller using first calculations. We have verified our calculations in the MATLAB, tuned based on two parameters of our controller, the gain and also the zero. The gain didn't help much, but the zero location shifting from 1.34 to 2.52 was very helpful, and we see that the specifications are met using this controller. Thank you again for your attention, and I hope this clarifies the situation for you and for this Root Locus method for our PID controller. I will continue with the PD controller and also for the PID controller in the next videos, so keep in touch, and if you have any questions or comments, please let me know, and I will see you next time. Take care.